first of all, I think that I share with in the chat with a link to our current tool that we are going to use. And for you that don't know this tool, this is Google Colab, and this is a Google Colab notebook. Google Colab actually is a free tool that allows us to run Python code from the web up from scratch. You don't need to register or anything. You just can use it with your Google account. And it also allows us to have virtual machine for ourselves. It is in the background Jupyter notebook service that requires no use, no setup. And we have actually assigned memory and disk space and like an archive system, everything without needing to do anything. This is my notebook, so if you want to make changes on it, you just go to your file folder and put like save a copy in Drive, and it will save in your own Google Drive. If you don't have a Google Drive, you can make an account of it. Then you will be able to edit. But anyways, if you don't want to edit, you can still play around with this. So let's start with the workshop roadmap. What we are going to do, since this is like already running machine, we are going to install Tesseract. That is the OCRing tool that we are going to use. I forgot to mention that in this workshop, we want to recognize license plates and then extract the data from those license plates. So for the OCRing part, we are going to use Tesseract. And then we have a repository that we have in GitLab that has a pre-trained machine learning model for YOLO, and some of the code, again, you can play around by yourself. And we have also some Python dependencies. Those are all the prerequisites from our machine. If you have here the prerequisite section, and you just press play, it will install everything in a couple of minutes. If you see here, I already have everything installed, but it doesn't take more than a couple of minutes. And after that, after installing the prerequisites, we are going to go to two different parts to achieve our goal. That is a detection and extraction. First, we want to find in an image license plate. Then we want to isolate that part of the image where the license plate is. And then we want to run extraction process to get out the text of it using Tesseract OCR. So let's get started. For the install the prerequisites, we will need Tesseract OCR that is not installed in our machine by default. We need to clone our repository and then only install two Python dependencies that are OpenCV 4.5 and PyTesseract that will allow us to actually communicate with Tesseract. That is a library that is not only for Python. We have Python bindings for it. So if we can see here, actually you see that you can run command line codes, so it will be like a machine. If I will just run this at this moment, it will tell me that I already have my data checkout. Then we need to clone the repository, and this repository is where the machine learning models are. And then we need to install the Python dependencies. Once this has been done, you have at the left side a nice navigation bar where you find like a folder. And if you click there, you actually will see your directory system in the virtual machine. These machines, by the way, will be available to you as long as you use them. And after some time that you are away from the keyboard or not using, they can be recycled. So the things in this file system will be removed, and then you will need to run your notebook again. So you see here that we have our folder with the Git repository, and it has two folders and some files. In the data folder, we find, first of all, weights file that is our pre-trained machine learning model. The names file that actually has the list of all the objects that our pre-trained model can handle. In this case, it's only license plates. and some configuration file we use for working with YOLO. In the image folder, we have two pictures that we are going to use to test our extraction code and detection. We have some document images that we use in this notebook, and we have two files with Python code, detect and extract. We are going to go through the detect part that uses machine learning just to explain what's the idea behind and let you play with it. And we are going to write our extraction code and explain step by step what we are going to do. But you also have like a extract version here for you to play with it. And then we have just utils class with some handy methods that we want to type over and over again. So let's get started. So we start with the detection part, and we see here that I draw a small roadmap about what we are going to do in the detection part. In the detection part, we first need to load using OpenCV our train model plus the YOLO configuration file, and that will generate for us an OpenCV detector. This detector needs an image as an input to detect the objects on that image. So the first thing we are going to get is our image, but then we need to convert this image into a blob that it's a group of connected pixels in a binary format that is actually the way it needs to be input for the detector. Once we do that, we will run the detector and we will get a set of predictions. That means it's like a collection of regions of interest, of areas with predictions values saying the objects that were found and the accuracy of the prediction. After that, we are going to simplify the overlapping results because predictions usually come in sets, so there are going to be several that probably are overlapping. And that will end up with regions of interest, so the areas where the things we are looking for are. In this case, it's just license plates. We are going to output two things. The first one is the full image with the region of interest shown. So we show where we found the license plate. And for that, we are going to use a class file that has the name of the objects that we find. In our case, since we are only training our model to find one object, that name will be license plate. But if your model is trained to recognize different type of objects, you will need a class file with the names of each of those objects, so then you can correlate the findings with the name. And then we will save our crop region of interest in another file that we will use as input for our next step that will be extracting the data out of the license plate. Okay, so let's get started. First of all, we are going just to take a look to our detect file. As you can see, also Collab allows us to, in live, edit our code and see it as both like an IDE. Actually, it's not only highlighting the code, but also allows us to type and predict what we want to have from different objects. It's very nice. So as I said, I will go just roughly through the detect method because it has a little bit more complexity based on the machine learning part. And then we will go a little bit more in depth in the extraction part. So first of all, we have our main function where we will pass a file name that we want to use for detection. Then we have a detection config class that I use to save some information where my classes are. Classes, as I mentioned, were the names or labels for the objects we train our model, where our model is also located, the configuration for YOLO. Then these are some configuration values we are going to discuss a little bit in the future, and these are just colors we use to show the regions of interests. So the first part of our process is load the detector. For loading the detector, I have a convenience method here. That's a low YOLO detector that will allow to just using OpenCV to read the convolutional neural network given a path and given the configuration path and the weights path or the train mode. The second part of it then is reading the image that we want to actually make use of. And then we are reading also the labels for the objects that we can find. As I said in my previous explanation, we really need for this convolutional neural network to work, the image transformed in this blob that is a group of connected pixels or regions in a binary image. And then we need to set them as input from our detector. Once we set them as input, then we are going to get output layers or like predictions with different regions with different amounts of accuracy found. So I have a convenience method for this. It's just a detector getting the layers name and asking the detectors to output the layers. These are going to actually return to us a certain amount of regions or coordinates where the possible objects we are looking for are located. So once we have our predictions, we are going to get the boxes for those predictions, the level of confidence of the model, and the IDs of the objects. That means that if, for example, if I have 80 different objects, and let's say that cat is like object 0, I will get like the ID 0 if it finds a cat, if I will get like ID 10 if 10 is a car or whatever. So I will get a list of different regions, how confident is that the object that it actually found is the object that thing it is, and the ID of those classes so that we can correlate with the name. Then what will happen, I will just switch here, is that usually we will get a set of regions of interest that overlap here. For example, if you see this image, you will see that the person is being found like 3 different times, and it has different levels of confidence. But we, in the end, want to remove all the overlapping boxes and just get the best of them. And the same for the dog. So we apply a non-maximum suppression algorithm that it's a little bit hard to explain at this moment, but in like a nutshell is selecting the best boundary boxes for the object and rejects or suppress all the other boxes that are not the best match. So in the detect part again, we will go here, and we have the indices or the best matching candidates for the objects we are looking for. After this, we have coordinates, and the coordinates, we are just going to get the x, the y, how width, and the height of the object, and then we will crop the image. This is our original image, and we are going just to crop it out, and then draw a bounding box on top of it. We have a convenience method that allows us to save the image, and we will call it detection ROI. And we have again going to save the detection crop. So what we are going to do is in the original image, draw a box around our found data. And then also we are going to crop the image and save it separately for the next step that we are going to do a little bit more in detail. So after reviewing the code, then we have here the execution of the code itself. What we are going to do is make sure that we are in the folder with the code it is. And then we are going to execute Python, our detect code. We are going to feed one of the 2 images we have as sample here, this car1. And what we are actually going to do is in the same line execute Python code to show those two images. So if I run it now, it actually found the boxes where the code it is, and there we are. This is the image of our car. I forgot to show it. Taking a while to load, yeah, because it's big. Yeah, you see, this is the original one. And then we have the region of interest mark in the original file. This is quite a big image. This is the size in pixels. And then we have our region of interest crop. Those are the two files. So now we also have a new folder that is called out. And the folder will have the detection crop and the detection region of interest. So if we open it, actually it's the image that we just saw in the code. So this was the part of the detection. So let's move to extraction and go a little bit into it. So what we are going to do in the destruction part? Well, now that we have actually the area that we want to start looking into, that's our crop region of interest, we are going to go to like 4 stages before we can actually extract 3 stages and extraction itself using the OCRing tool. The first of it will be pre-processing. So we take the image, reduce the amount of information, make it clear, well, reduce the amount of information, but grayscaling it. We resize it a bit to make it easier for the OCRing tool to extract the text out of the license plate. We blur it just a bit to remove any possible noise that may happen in the image. We threshold and dilate the image, as thresholding allows us to mark a little bit more the boundaries of different objects in the image so we can extract them, dilate them to make their areas a little bit thicker. We are going to detect all the objects in the image using counter detection. Then we have a little set of regions of interest, different objects that are in our license plate that may be something that we want to use. After that, we are going to do some small heuristic filtering. That means just using plain logic to understand how we can actually filter those objects, the ones that we don't want from the ones we want. And in the end, we will end up having individual regions of interest, each letter in the license plate. We will invert them because for the thresholding, we were using the inverse binary image. So we will get it back with white background, black foreground. Blur it a little bit again to remove any noise. Send it to the OCR engine to extract, and then show the license plate number. So let's get started. For any of you that want to run it, you can actually do this, but we are going to write some live code here. So I'm going to start, a little bit below. You can, So first of all, we will need to use PyTesseract and also OpenCV. And and we also have utils method that will allow us to show the plot image. So our first step will be reading the original image. And for this, what we are going to do is create a variable and use OpenCV to read that image here. And then just put the location of it. It's in data, out, detection, and crop. Keep back. Yeah. Okay. Once we have this image, as I say, we need to convert it in grayscale. because we really don't want all the information that comes with it. So for that, we are also, again, using OpenCV. And it's like CV2, CPT color, if I remember well, image, the original image, and then we are going to transform from color VGR to gray. I'm not sure if I mentioned, but OpenCV images are not RGB, they are VGR. It's a little bit twisted, the colors. So once we have our grade size image, what we are going to do actually is resize it, make it a little bigger, so it is easier for the extraction process to work. And we are going to do it 3 times bigger what it was. It also, we will have interpolation, and it will be CV2 interpolation cubic, intercubic, if I'm not wrong. And then we are going to show what we did just to make the graphs of it. Great image. So if we run this now, we will see the image that has been loaded and converted to gray. So let's keep executing. So as I said, let's go back to our roadmap. We say grayscale, resize, and blur. So apply blurring to remove any noise. In this case, we don't have a lot, but still it's important to do it because we don't know the quality of the images. So we are going to do, medium blur. And for the medium blur, we are going to use our grayscale image and convert it with matrix of 3, blur, and then we are going to put our blur image there. So after this, what comes here is thresholding and dilating our image. So thresholding, actually, it helps us to partition the image in different segments so we can recognize individual objects on it. So for that, we are going to use thresholding method, CV2, threshold, yeah. And we are going to take a blur image and make the cut process, and we are going to use a specific thresholding method that it is Otsu. As Daniel explained in theory, thresholding is the cutting point where all the pixels will turn black or all the pixels will turn white. And if we do just a normal thresholding, what will happen sometimes is that if the image has too many different areas with shadows, it could get too dark or some of the information get lost. And the type of adaptive thresholdings would allow us to take decide which color will be black or white, depending on each specific sub area of the image. So it will be better. So pipe and then CV2, because we also want not only to threshold it, but we want to threshold it inverse binary. That means that our whites will be black and our blacks will be white. And then we will show the plot of it and threshold, and we'll show this. Okay. So let's run it and see how it goes, if I haven't made any mistake. Okay, so you see here the blue version really does not change a lot. And you have the threshold version, binarize invert. That means that all the black pixels convert into white and the other way around. Cool. So let's continue. After the thresholding, we want to apply dilation to enhance a little bit our area. And for that, we need a kernel. The kernel for dilation, it's a little bit hard to explain, but it's a mathematical process where we are going to multiply each one of our pixels to change their neighboring areas. So in this case, we are going to get structuring element that actually is getting a kernel for our calculations. Correct, if I'm not, yeah. And then we need kernel size of 3 by 3. This at the moment, it's a little bit hard to explain, but just take like this. It will help us to thicken out a little bit our image. So for the dilation, we are going to use a dilate method. We need a threshold image. We need our rect. And we also will need a number of iterations. But it's going to be only one. And then we are going also to show this here, just to see how it goes. And then once we have the image here dilated, we want to start extracting the different objects in the image. And that's why we are going to create, find the contours of the image. For this, find the contours of the image. For this, we are going to use contours. We're going to use a CV2 method that is called find contours. What this method will do is return a tuple. It will return the contours at the hierarchy. Sometimes there are objects embedded in other objects. And also for us, it's important to know the hierarchy because we want like the higher level contours, not the inner elements of it. So what we are going to do is use the dilated version of the image. This is read tree. This is the tree of contours means we have a hierarchical representation of elements in a matrix. We don't need to care a lot about that at this moment. And it's a change prox simple. Okay, so once we have all the contours, we just need to sort them out. Sorted contours. And for that, we need to use the sorted operation just to have the higher level contours and forget about the rest. And we have like a lambda here. This is again, don't worry much about this. It's just filtering a little bit all the bounding boxes around different objects and just getting the higher level of them. Bounding rect. And it should be, yeah. It's this little bit, okay. So once we have all our contours, we actually have found different objects in our image. Let's show them a little bit because otherwise it's a little bit difficult to image. So we are going to iterate all these contours. Contours for each contour, for contour in sorted contours, sorry. And what we are going to get is for each contour its location, x, y, width and height, CV2, boxes, boundary rect, sorry, for each container. And then we need to draw a rectangle on top of the image so we can show actually the objects we have found. In this case, we use CV2, sorry, rectangle. And in this rectangle, what we are going to use is, I forgot to put it here. I'm going to make image rows. I'm going to create a new image, so I'm not going to draw on top of my original image. I will just copy it. So I will draw on this, and it will be in XY position. It will then I need to the initial and end point of it. It will be X plus width and Y plus height. And then I need to use a color here just to show. Let's use red. This is RGB colors, and then just the width of the bounding boxes to show. So it's too big. Let's do 4. And after that, we can show plot and bounding boxes and yeah, image rows. Sorry, image row. Okay, let's try to run it, see if it does not file. Okay, this is the lambda one. What did I wrong here? We have contours. Okay, now, okay, I mistyped lambda. It's running, cool. So we have our gray version, the blur, after that the threshold, after that oh, sorry, I forgot that I actually resized the image. So the original image we have here has been resized, so I'll take this one here, and yeah, image rows, because the coordinates are based on the original image. That means that they are like out of size in this moment. So let's play it again. Okay, and we see here that we have different objects of regions of interest, but it is a little bit too much. So if we see here, we can see also we have the letters that we care about, but also we have all these small points. We have even like bigger bounding box. We have all the stars of the European Union and these letters that we don't care about. So at the moment we have using machine learning for detection. We are using morphological operations to then find different objects in the image. But after all of this, we still need to use our common sense, logic, or heuristics to think about what we want to filter out from this. So I have like here a sketch of the image, and we say, well, I have all these other objects I don't care about, so I need to filter them out. How am I going to do it? Well, I came up, this is like just empiric solution, that the regions that I care about should be at least 1/3 of the total image size. So that will filter out all these small dots here. And also the aspect ratio between them should be 1.2. That means that it needs to be taller than wide. And we can also have a minimum area, because sometimes maybe the aspect ratio is that, but still is too thin. We don't care about it. So what we are doing here now to do is like lower down or filter the amount of results. Here in this part is The heuristic filtering, that is just a fancy word to say, well, I need to think how I'm going to filter this using some common sense logic. And this is very common in computer vision. There are a lot of different things we need to join to have a complete solution for it. So let's go here in our part. So we have first of all in our list, yeah, we have first yeah, in the heuristic filtering, we have the aspect ratio. That's the first part we are going to do. So for the aspect ratio, we need to know the full size of the image. So we have the height and the width of the full image. And we are going to use a method that is called, well, it's actually just a property from the image that is shape. And this property will actually, it's a tuple that has 3 values. If it's a color image, it will have the height, the width, and the color depth. So we don't care about the last one, so I just put like an underscore there, not make use of it. So the first part of it is like the aspect ratio, right? So I will say the ratio equals the height of the current region of interest divide the width. And well, this is I don't need the height and height of the image for that. And I will say that if the ratio is less than 1.2 or the ratio is too big, also bigger than 2, I just will skip this one. And then we also don't want that the box is like bigger than a quarter of the whole image. So for that, what we will do is if height divide the height of the current region of interest is greater than 3. I will also skip it. I will not continue. And then we have one more that it's what was it? Maybe we can just get it here. So let's run it and see where it gets. So that's all the regions of interest we have now. Execute the code again and see if it improves. Cool, much better. Now we have only the letters. All the other elements have been removed. So we can also add a little bit more. We can add the total area of the object, but in this case, it worked quite well. So after drawing the rectangle, what we actually want to do is to get these regions of interest, the small images, and pass them to our OCR engine to read them, because that's our final goal. So what we are going to do is get our ROI or ROI image. Let's call it like this. This is actually the region of the image of the region of interest. What we are going to do is use our threshold image and put it in small piece that we want. So we are going to have y and y plus height, and then x, and then x plus width. And that will take us like a small bit of it. But we don't really want to just cut the letter. We want to take a little bit more just to be sure that we are getting the whole of it. So I will set up like just arbitrary padding. And what this arbitrary padding will let me do is like cutting a little bit more at the size of each image, so I have a little bit better grasp. So white minus padding, white plus it's like minus padding, height plus plus padding. And then we have x minus padding and x plus width plus padding. That should give us like a little bit better view here. And then what we are going to do here is, now that we have it, we have the inverse version. You see here, this is the current source of our crop. So we are going to invert back to its original form, and this is going to be CV2 twice not, that will revert it, and it will be the raw image. So we have the original not inverted version, and we are going to be a little bit conservative and are a little bit of medium blur. That's just, again, removing a little bit of noise. So raw image, and then we are just going to leave 5 as the kernel that we want to do. So just to show this for instruction purposes, individual letter, and then we can do this and see if it works. Okay, what was it? Oh yeah, there's a wrong character there. Yeah. You see all the individual characters being extracted. So it's quite a lot. Well, and this moment I would just like comment it out because it's too much to show. And then we are going to get the text itself. So for that, what we are going to do is like plain text here, have initial empty variable, and then what we are going to do is have like text equals tesseract, that is a tool to call our OCR tool, image to string, that will transform. I will read our image into one string, and then I will do raw image, and I will give a configuration value to tesseract. Give me a second. This is, I need to copy and paste because it's very long. But essentially, we are going to tell Tesseract that we are not working with any specific language, because in this case, we really don't care about language. And we have a wide list of characters. So we are only going to tell our OCR machine that we are only caring for numbers and letters. And then we have our text. So what we are going to do then is from the play text, we are going to join it in text, and in the end we are going to print it out. And let's see if it does not explode. Cool. So let's see, and we have here P5, 8, B, PS, and we finally did the whole extraction live. That's pretty much it to show it. So as you saw, in any case that we apply computer vision, usually only one solution or one approach is not enough. We need to join them together, and in the end of that, we need to work a little bit towards heuristics or like common sense to make a little bit more filtering of the data. And the very important part of this is the pre-processing, how I prepare the image to get recognized. And of course, tools like the OCR tools are also very essential, but then can vary in quality. But it's up to us to make the most perfect image before sending it to tools like the OCR instruction part. In the end, you can use this code for yourselves, copy it. We'll share with you the link with a train YOLO weight for more than 80 different objects and class names, so you can interchange it here and just see how it works and play with it and try to find other objects. YOLO is quite fast, even works in live video. Although the OCR instruction does not work in live video, so you cannot extract text live, but you can recognize objects live. Thank you very much for your time. I think that this is the end of the presentation, and then, of course, we're open to questions if there is any.
Hey there, Rodrigo. Well done. Hats off. Live calling like that. Whew. You don't see that often, right? There are a few questions, but they were actually also for the previous presentation already, and I just missed them. So one from Alexander, and he asked, in which use cases do you use a natural language processing model alongside the image recognition model?
Sometimes you need to classify what the content of a document it is, but then first you need to extract the text from different regions of interest, and then you went to like a natural language processor to understand what it is. So it's usually used for classification. There are sometimes like documents that are not pure text, so you first want to recognize where those hot areas are, extract the text, and then send it to classification process. Cool. Or natural language process. Yeah.
Nice. Sounds good. And then another question from Carlos. Do you also have a way to filter out small patches of pixels once the image is in binary? So to remove connected pixels that are less than X amount of pixels in an area?
I think that it really depends, right? So the thing is, usually what you do is if you have small patches of pixels, I'm not sure if you mean noise by that, but let's say that, for example, you have some grains or some dots left in your picture after you optimized it or binarized it. Something that you can do is one of the techniques that we've discussed is erosion. In this case, you would use, or dilation. It depends on which binary pattern you're having. But what you can essentially do with erosion or dilation is, if you have like really small dots of noise still left in the image after binarizing, it is possible to either erode or dilate the image. And what will happen then is that these little dots will sort of be swallowed by the pixels surrounding it.
Yeah, so one of the use cases, sometimes you want to split two objects that are very close to each other. And when you do the thresholding, they have like some small bridge between, so it's not possible to detect them individually. It's like just a big bulk. So if you apply erosion, then you just cut a little bit the borders of it, so make them split. So erosion is one of the ways to remove these small areas, patches that connect to two different objects.
Yeah, he's basically asking that because he answered now, yes, noise basically to erode without affecting the letters or numbers.
Yeah, the thing is that you probably, you will hit the numbers if you only do erosion. But what you can do, for example, is just imagine that you have, for example, some black dots, and then your background is white. So if you want to filter out those black dots, you would dilate the white dots so that they sort of swallow these black dots, right? But then, of course, also you chip away a little bit from the letters or the numbers, like you mentioned. So what you can actually do is, after you've applied dilation, if you then apply the opposite again, because the dots are already gone, so they won't come back. But you can make again the letters a little bit bigger again, so you can sort of bring back what you took away after you removed the dots. So this is the process. I think it's called opening and closing. It's
Yeah.
also something that's part of OpenCV. So it just means erosion followed by dilation, or the opposite. So dilation followed by erosion.
Cool. Cool. Sounds great. And there's another question, and that's asking for a friend. If you're a complete newbie in computer vision, where should they start?
That's a hard question to answer, but I think that the steps that we explained for us, we learned them, but not in this order. I will say maybe go with already trained machine learning model just to see results fast. So you don't really need to understand fully how it works to see results. And then start thinking about these basic morphological operations we explained, and what you want to achieve. Do you want just to detect things? You want to detect them, crop them, and then, I don't know, get some information out of it and then work from it. So, but I think that starting with machine learning models gives you really like a feeling of like achievement. You are doing something. It's not that hard to start. And then you say, well, what I can do next? And I will say that for morphological operations, text recognition is one of the best starting points.
Great, great. It's very nice to have you both here. These were the questions. It's also good to see that the cat is back. So the cat is back again.
Yes, she's asleep now.
She's asleep now. Perfect, perfect. So then, yeah, you guys did a really great job. Happy to have you here at Build. Then we have one insider information still left to tell, and that is the 23rd of February. We will have the next Tech Talk session where we will talk about how to build, host, monitor, and debug containerized apps in Azure. So if you want to be there, there are two ways to do that. So you can go to the meetup link that will eventually be posted inside the comments of the YouTube link, and also on Twitch, I see. And you can also hit a nice subscribe button, which is somewhere there, I think. So enjoy. I hope you all enjoyed it. Please give a round of applause for our speakers, and you can do that in the chat. They will be happy to receive them. And that's it for today. Thank you all for joining.
Thank you very much.